Hello, everybody. Welcome to the Virtual Summit 2021 Data Platform, Scaling Clustered Column Store. My name is Thomas Grohser, and I will be talking today about how to get Clustered Column Store to perform really well. If you just use it, it works great. But if you follow a couple of very simple rules, it performs even better. And this is what this session is about. So welcome, thank you one more time, and let's get started. My name is Thomas Grohser. I'm with SQL Server for 27 years. I started when 16-bit was top of the line. Now we arrived at 64-bit. The last couple of years, I've been a Microsoft Most Valued Professional, MVP, and I spent my time figuring out how SQL Server can work better, faster, more secure, more reliable. And lately, I also spend a lot of time in automating it. I'm speaking for over 12 years at conferences like this, and here's my email address and my LinkedIn contact. If you have any questions that come to you after this conference, feel free to email me. I do my best to answer. So what we're going to talk about today. How does clustered column store work? This is the first one. We have to understand a little bit how it works. We're not going to go into like a deep dive session on it, but the basics so that the rest of the session makes sense. Then we're going to talk about how to help clustered column store to be more effective. This is the main part of the section. And then since this is a virtual session, all the questions are at the end. As I understand it, since I'm recording this many weeks in advance, I will be able to answer chat questions while this is playing at the conference. So right now you might be able to ask me questions through the chat or not. I really don't know. But we'll do our best to make this work in this world that we live in today. So let's get started how clustered column store works. And before we can talk about clustered column store and how it works, we have to look a little bit back on how a regular row store worked. So in a regular row store, SQL Server stores row by row. It starts with a row header. This is a couple of bits that tell SQL Server what to expect in that row. And then it's followed by all the fixed length column and the next column. And then at some point it converges to the variable length columns. But basically the row is one stream of binary ones and zeros. Everything that belongs to one row is stored in one block of memory. Yes. And then the same goes for the second column, second row. And as you can see here, column C is a little bit longer and D than they were before. And that's how it's stored. So these individual rows are then grouped into pages in SQL Server. A page is 8 kilobytes, uses 96 bytes at the top and a couple of bytes at the bottom to manage the page. But then basically the rows are in random order on the page, however they fit. And then there's a little slot array at the bottom of the page that points to where the rows start so that they don't have to scan through the page every time to find a specific row. Yes. And then the next row and the next page and the next page, and they all look the same. The important part is if you need one column from one row, you have to read not just the whole row, but the whole page that contains the row into memory. So if I need the 5 bytes that are stored in column C in the first row, I need to load all 8 kilobytes into memory and then find them there. This is row store and it works pretty well. Don't get me wrong. It's not me criticizing it. It's just me explaining how it was. And in a lot of cases, when you need many rows and all the columns in each row, that storage format is just fine. But especially in data warehouses, we often have the problem that we have a very wide fact table, many columns, and many rows, and we only want to we create a query that only like accesses 2 or 3 of these columns at a time because we want to slice the data by product and then we want to slice it by customer and not both at the same time. Yeah? But in row store, we have to read all the data, and in column store, we don't. And the next slide will immediately show how this is different. So in column store, column A, that's the first one in our table, and then all the values for each and every row are stored in one unit. Yeah? And this will be called a row group, as we will learn soon. And then the second column, and the exact same thing. All the values for several rows are in one thing. And then C, D. So if I now want only column B, all I have to read is that vertical block of data for column B, and I can ignore A and C, and they can stay on disk, and I never have to bring them in memory, and so on. Yeah? So these values for one column that are in one group is called a row group, and that has roughly 1 million entries. We will learn the exact number soon. Yeah? And if you have more rows than that, SQL Server starts a second row group and a third, and you can have millions and billions of these row groups. Yeah? That's how this works. Okay, so if you're interested in more how the bits and bytes and everything happens in a column store, there's an excellent presentation from Bob Ward. And of course, there is Nico's collection of, I don't know how many hundred of blog entries about column store that explains each and every bit. So that's for future reference. A little bit about column store history. This is a product in the making. It's still getting better with every version, and it started in SQL 2012. You could create a column store index on top of a regular table, and it was read-only. So basically what you had to do is every day you would drop the index, load your data warehouse, and then recreate that index, and then use it all day long, and then start the process in the beginning. Lots of people did not like that because once you have a lot of data, creating this index can take a lot of time. So Microsoft enhanced it in 2014. They created a clustered column store where the column, once you create like with a regular, when you have a heap and you create a clustered index on top of it, the clustered index becomes the table. Yeah? And the same happens with a clustered column store, and that's why they call it clustered. It becomes the table, and insert, update, and deletes are possible on this one. We will learn that there are many restrictions on that, but at least it's possible. 2016's also made it possible to edit and remove if the column store is a secondary index on top of a regular table, so that read-only restriction gets completely removed. You could have filtered secondary indexes so that you only index a part of your table, and you could now create regular indexes on top of a clustered column store. So the other way around, you have the column store at the base table, and then you can put on. This comes with a warning. I'll tried it, and it usually doesn't go well. Because once you start using clustered column store and get used to the massive amount of compression, I actually had a case where the column store, the actual table, was smaller than the index on top of it. So the index became the majority of storage space, and it just didn't make sense. But it's possible. And there are always cases where it makes sense. Yeah. Yes. 2017 added computed columns to clustered column store, so that's good. And very importantly, in 2019, you can now create and rebuild them online, like every other index in Enterprise Edition for a long time. So that helps with maintaining very large tables. Yep, same restrictions as with everything else. You need the extra space while this is happening, and it takes a little bit longer than just doing it offline, but it enables you to do it while the system is still accessible. So that's for the history. Let's move on how to make it more effective. Yeah? So if you just use column store take your table, make it a column store, it works. No question. But Microsoft built a lot of optimizations that only work under certain circumstances, and this is what we're going to go through today. So the first half is going to be how to insert, update, and delete data, and the second half is which types of data to use to make it most effective. Good, so let's get started. So the goal is to build a column store fact table that returns results quickly, even if we have billions and trillions of rows. And to be very clear, clustered column store is not a tool if your table has 3-4 million rows. That's not where its effectiveness comes in. Clustered column store and column store in Bing is made for billions and more rows. 100 million, that's where it starts to get effective. Maybe 50 million, at the very lower end. Everything below that, you will probably not see the magic results you're expecting. Once you go into billions and trillions, you could not do that with a regular table. So that's what it is. So the solution. We must help column store to be as efficient as possible. That's the whole goal. Help it. If you have choices, make the choice that is better for column store to work at. So to start with, we need to give it a nice physical database to exist in. We need to insert data so row groups are created perfectly and not as a compromise. We have to partition column store. It's the only type of index that actually gets much faster when partitioned. We have to use the correct data types to make all that happen. So first, the database. That's the easiest part, but it's really hard if you don't consider it from the beginning. Under the covers, column store is stored in a regular table. This might sound weird, but what Microsoft did is column store, each of these columns, each of these row groups gets super compressed. They do a couple of other things to it, and then they store it in a var binary max table. So each one of these row groups is one row in a regular table in one column. So if they need to read 20 row groups, they have to select the 20 rows from the regular table. And for the veterans in the room, we know the moment there's anything involved that has the word max in it in its variable definition, so var binary, var character, national var character, something like this, it always becomes a nightmare when it comes to database maintenance. Why? You practically cannot shrink data files that contains a column store or any other binary large object like varchar max or var binary max. When you have you can theoretically shrink it, but for every page that needs to be moved to make the shrink possible, SQL Server, I think if I'm correctly, has to do a full scan of the whole table. And again, we're talking about a table that is built for billions of rows. So if every time you move one data page that contains this data and you have to read billions of rows, that doesn't work well. So the only way to do this is that you actually have space at the beginning of the file and then rebuild it into there, or you rebuild it into another file group. So you have to understand that. And for that, my tip is put column stores on its own file group. You need to plan ahead and make sure that put them on their own file group where you put nothing else but this, so that in case you need to kind of change that, you can always create a new file group and move it over there, and then drop the original one, so that you have a tool, and give it at least 12 to 24 data files so that each one is smaller and might not have the need to shrink that often. It's much easier to manage 12 small files than one large file. Because for 12 small files, you always find a space where to put them. For one large one, maybe not. Yeah? And it allows you also to scale a little bit better when you have independent drives where you can put them. Yeah? So that's for the database, nicely important. We're good too. It's easy to change at the beginning, but once you have a couple of billion rows on the table, changes like this become cumbersome. So plan ahead, just put it somewhere separate so that it doesn't interfere with other tables, and you do your normal table maintenance and normal data file maintenance as you do, and column store is extra, you basically don't touch it. Yeah? So that's that. Let's start with inserting data. We have to get data into our table. So we created a nice little empty clustered column store table. We defined it, and Books Online will tell you all the syntax about that. Yeah? So for inserting data, you have to meet one of your two new best friends. This one. And this friend is the number 1,048,576. This is, for all the math genius on there, this is the power of 1024, the power of 2. So if you take the square root of that, that is this. Microsoft chose this as the size of a row group, 1024 times 1024. I refer to it as a mega rows, like in megabyte. Yes. So you remember at the beginning we talked about these row groups that SQL stores the data in one. It's this amount of rows that go into one row group for each of the columns. And the idea is to insert exactly that number of rows every time. That is the perfect scenario. Yeah? If you insert less than 100,000 and 102,400 rows, that's also a magic number, so that's 1,024 times 100, then SQL Server in the background creates something they call a delta row group, which is a regular row store table, and then they union the two together. Yeah? So imagine you're inserting one row at a time. Every time you do that, they create another entry in the delta row group. And unless you rebuild the index, this is most likely not ever becoming an actual column store. So you define the column store, but you're not actually ever using one. Yeah? If you insert a couple of 100 or 1,000 rows at a time, you get a little bit. Thing is, if you insert more than the 102,400 rows, but less than the 1,048,576, then you get an actual row group with all the column store compressions and optimizations, and the data is actually stored in columns and not in rows anymore. But not all the available slots in that row group are used, so you're basically wasting not space, but since it gets compressed away, but you're wasting the ability to compress based on each other. So, for example, when you insert the same number in a column over and over again, and that is not that uncommon in a data warehouse. Imagine a column like country. Most country IDs will be the same because you operate in a specific country. Yeah? So what column store would do is says, oh, there is 1,048,576 IDs of the same value. All I have to do is store one of them, and remember, it's the same everywhere. Yeah? But if you only insert like 500,000 rows, you need two of these entries. So it takes longer to process. So long story short, the ideal way is to insert the whole row group in one go if possible. Yeah? If you insert more than these number of rows in one go, SQL will create the first row group using all the rows there, and then take the remaining rows and move on to the next one, and the next one, and the next one. So, with other words, you can insert 1,048,576 or any multiple of it. Yeah? 2 times, 3 times, 4 times, it's just fine. It's the same as doing one of them at a time. Yeah? So that makes no difference. If you insert any random number that is bigger, the last row group will have a small thing. Yeah? So that is still better than doing it row by row. So for example, if you do a daily data warehouse load and you don't want to have it very complex, just make sure you do it in one insert into, regardless of the rows, whatever you have in that day. So you're only wasting, and wasting is under air quotes, one row group that is not perfect per day. Yeah? That is probably acceptable. Yeah? But again, if you want to do it perfect, make sure all of them are. Yeah? And I already explained that. Compression is done within a row group, so 2 half-full row groups compress less good than 1 full one. Yeah? Very simple. You can, of course, clean up if you did the inserts wrong by rebuilding the column store index. Yeah? That will always clean it up and make it as good as possible. What I usually try to get is to this kind of insert architecture by not inserting into the column store directly, but into a two-stage process. So I have a process creating the data, and for now we have like one of them that uses the bulk insert API of SQL Server to store the data in memory optimized tables, in memory OLTP tables. You can use regular tables if you don't want to use in-memory OLTP. In our case, we usually insert so fast that these tables actually help us. And then we have a SQL agent job that waits for the magic number of rows to be there, just counts them, wakes up every second, counts it. If it finds the number row, it batch inserts them into the column store and then deletes them from the in-memory table. Yeah? And the column store grows over time, but has perfect rows. And this part is happening in SQL Server. This part, the creation of the data, is usually happening outside of SQL Server. Yeah? And that allows you to do all the processing, the normalization, everything outside of SQL Server, not wasting any kind of resources there. Over the time, we even optimized the process a little bit more. Because what we were doing is, and this will come later, that we wait for way more than this 1 million rows and pre-sort them before we insert them into column store. We get to that a little bit later when we go to row group elimination. So we talked about how to insert data. Let's talk about how to delete data, which sometimes have to happen. Data is not deleted in a column store, period. There's no delete function inside the actual column store. So what happens is that, as with the Delta row groups, SQL Server is just creating a little table in the background and stores all the rows that need to be deleted. And then every time you query the table, they make sure that they filter out all the rows that are in this table. So basically select where in column store and not exist in table that has deleted rows. And since a column store doesn't have a primary key or anything like this, they have to store each and every value in that extra table. And that's a row store. That's not a column store itself. Yeah? So every time you query something after you delete, you now have an extra condition in your query that gets injected there that removes all the rows that are deleted. So that is horrible for performance. Yeah? The only way to clean this up is rebuild your column store. So if for any reason you have to delete data, do it and then rebuild the index, because till you've done that, there is no nice way. Even if you delete all the rows from a row group, it doesn't remove the row group. It doesn't have that intelligence. Maybe Microsoft will improve this in the future, but for now, no. It just, if you delete 1 billion rows, they create a table with 1 billion rows in the background and then take the delta every time. So, updating. Okay. Everybody in the room, or in the virtual world where we are right now, that understands how updates are actually done can see the problem that is coming. So, how are updates done? Updates are not actually changing the data. Updates are technically an delete followed by an insert. So if you update one row, you first create an extra row in the delete table, and then you create a new delta row group with that one row to add it into your query. So going forward now, you have, whenever time you query the column store, you have to query the actual column store, the delta row groups, join and union these results together, and then remove the deleted part. And just imagine if you update data like every hour or every minute or just even every day, how much delta that is. Because if you update the same row again, there's now two of them in the deleted entry. And then if you update it one more, there's 3, 4, and so on. So single row inserts are bad. Deletes are worse. And updates are the combination of the two. Yeah? So the only way after you did updates, you need to rebuild the column store index. Again, there's no other way. It doesn't clean up itself after some while or magic time. It's just, you have to. And rebuilding that index on a very large table can take a lot of time. Yeah. So this was the 3 how you get data in. Technically, you can do the merge command, but since the merge is doing a lot of updates and single row inserts, I would not recommend using merge with column stores. But yes. Selecting data. Good and bad news. Column store is pretty good in reading through tables, especially if you filter columns and just pick certain columns. Bad news is there's only one access method right now for column store, and that's a table scan, full table scan. To be a little bit more precise, it's a full table scan with partition elimination if the table is partitioned. And this is why I said that column store is pretty much the only index that really benefits from partitioning. Yeah? You have to partition your column store table to help it not scan the whole table every time. Yeah. My recommendation is partition by the most common search criteria. So if you have something that is in every query, that's your prime candidate for partitioning. It also needs to be granular enough. So if you always have like male-female check in it, that's not granular enough. Yeah? That would basically divide your table in half, which still eliminates half the table to be scanned every time, but something like a birthday or a customer number range or a product group or something might be more suitable for this, because you wanna split your column store in as many partitions that make sense, and for that we have to have a look at how partitioning works. Yeah. So there's a 12,000 partition limit per table in SQL Server. That limit is theoretical. If you read the interwebs about partitioning, most people warn you that 3,000 is the upper limit that is practically working. Yeah? Everything above that, you're just inviting issues. Yeah? I myself, 3,000 worked just fine. Once we moved up to 4,000, it started to happen. Things didn't go well. Yeah? So my recommendation is stick around 3,000, and that's a plenty. Yeah? For example, if you partition on a day, you can almost store 10 years. Yeah? And I would even go for 10 years because hopefully 10 years from now, Microsoft has fixed the partition limits and 3,650 partitions would be fine. So if you go with days, that is a good start. But then all your queries should filter on that you're interested in a very specific day or range of days. Yeah? Another thing that I like to do sometimes is, if I can't find a single key that gives me enough granularity, I have created surrogate keys that allow me to achieve that. So let me show you this very simple thing is, I take the year, I take the month, and I take a product group and stitch them into an integer. Yeah? Year, 4-digit number at the beginning, month, 2-digit number after that, and then the product group is a number between 0 and 9,999. I'm just making sure with constraints this is not ever broken. and then stitch together that surrogate key, and that allows me to partition very, very nicely. It doesn't work if you have actual 10,000 different product groups, because then you exceed the limit of partitions. But if you practically have a dozen or so product groups that have all weird numbers, and then the year and the month, which gives you basically, let's say over a period of 10 years, gives you 120 partitions times another 10 product groups is like 1,200 partitions. 30 product groups still works. Yeah? Again, a little trick that I use. The idea is to have a nice, roughly 3,000 partitions, 2,000, 1,000, somewhere in that range, so that when you filter on it, the majority of the data does not get scanned every time. Yeah? So let's go back to the example with the date. If most of the time you need reports that cover one day, partitioning by day is perfect, because you will have the where clause where date equals this specific day, and then column store can figure out, oh, that's my partition key. I just picked the partition with the one date that matches and goes through. Even if you do by day and then you query for a whole month where day from to, it will only scan the 30 or 31 partitions that contain that month. Yeah? So that's very practical. And again, this is about helping column store to be more efficient. And if you only query a part of the data, that's more efficient than if you query all the data. Very simple concept. Data types, that's the second one, and that's the big one I see a lot of people not paying attention to. Yeah? Meet your new second best friend, new best friend number 2. Yeah? It's 8 bytes or 64 bits. Yeah? Every data type that fits in 8 bytes or less is your friend in column store. So column store loves data types that are 64-bit or less, because they can do a lot of optimizations if they basically can fit the whole data type in a single register of the CPU. So these are the data types that work: big int, small int, tiny int, datetime 2, time, float, binary 1 to 8, character 1 to 8, and national character 1 to 4, because they need 2 bytes per character, small money, and date. Technically, varchar something works too, but it's very short because it needs like 4 bytes to manage itself. And then that basically leaves you only like with 4 bytes, and if you make it national, it leaves you with 2 bytes. So that's why I didn't list them. Technically, yes, but practically, no. Yeah? So these are the ones that column store really likes, because everything fits in a register of a CPU. And even better, yes, we'll talk about how this comes in once we talk about batch mode later in the presentation. Filter pushdown. Yeah? That's the first one that works when your data is 8 bits, 64 bits or 8 bytes or less. Yeah? So when you select from a table where your column is has the values between 7 and 25. Yeah? In row store, what SQL Server has to do is load all the data pages from disk into the buffer pool, even all the data from columns that are not even mentioned in that query, scan the data, and return the value, add up the values for X, or select all the values for X, while checking the values for Y in each row. If you have a column store that uses more than 8 bytes, this changes to reloading just the columns X and Y and doing the same process. We have to loop through all of them and figure out all the Ys and figure out the ones that match, and then pick the X value to return. If we use column store with less than 8 bytes, what the query engine can do is it tells the storage engine, hey, just give me back the columns that match that criteria, and the storage engine will only extract the columns that are actually needed for that. Yeah? So we're only getting back from the storage engines the ones that already match the filter criteria. That's called filter pushdown. So instead of the query execution part, the underlying storage engine does the filtering, which means we don't have to shovel the data around and then process it again. It's immediately processed before it's shoveled around. So that saves time. Filter pushdown. The same goes for aggregate pushdown. If we change the query to we want the sum or the average from a certain column in a table, in row store, again, it has to read each and every row and process each and every row, then find the column X in it and add up and average out the columns. In column store, if it's more than 8 bytes, it only needs to read column X, which saves a lot. But it still has to do the aggregate functions after transferring it from the storage engine into the query execution engine. If it's less or equal to 8 bytes data types, then the storage engine just returns the aggregates. Yeah? And just imagine how much less data has to be moved around in memory if instead of, oh, there's a billion rows, give me each one of them. For this one column, give me the billion values, I add them up, or you tell the storage engine, hey, scan through this and just give me back the aggregate. Don't bother about the actual data. Just give me back the aggregate instead of the data. Yeah? And that's the difference. Yeah. Row group elimination. That's the next big one. Yeah? So we pushed on our filters with things. Yeah? We already eliminated a lot of data with partitioning, but we can eliminate more with row groups. Yeah? For all the columns that are 8 bytes or less, very simplified, Microsoft keeps a min-max value what's inside a row group. So if you store all ones on the first day in your row groups, and then you store all 2s and 3s on the second day, and 3s and 4s and 5 on the next day, each row group, the first row group will contain, hey, min and max is 1. The second one will have min is 2 and max is 3, and so on. Yeah? So whenever they scan now through row groups, instead of opening up the row group, uncompressing it and scanning through it, they just look at, hey, what are the min and max values? There's a filter. We only need stuff that is equal to, let's say, 4. So the first row group, min and max is 1. 4 is much larger. We don't look at it at all. We don't have to. Second one is 2 and 3. Nope, that's still too small. We don't have to look at it at all. The next one, 4 and 5. Yeah, that one we have to open, and then we can push down the filter and just return the ones with 4. So row group elimination, same as partitioning, makes column store not read data where it immediately knows it cannot contain the rows and columns that we need to satisfy the query. Yeah. Here's the same example in written form. You can read through that on your own. Yeah. So the tip for that is, and this is when I said in the beginning, we optimized our insert technique better. What we do is we pre-sort large groups of data by a second one. So we insert 1,048,576 rows per partition at a time. But what we also try to do is by a second, not by the partitioning key, but by a second key that we filter on a lot of, we pre-sort the data. So instead of waiting till we have a little bit more than 1 million rows to insert, we wait now till we have like 50, 100 million rows, and then sort them by a secondary column, so that within the partition and the secondary column, we have all the same values or most of the same values within one row group, which allows us to eliminate row groups very, very efficiently. So for example, your partition would be on the date. So every day you insert into a new partition. That's great. And then you would sort the data like by product ID. Yeah? And that means that all the data for one product are most likely in one row group or in 2 or 3 row groups. And so if you filter on the product, all SQL Server has to do is look at the row groups that have that number for your product in the row group header. that says, hey, min-max of this column is here, and can ignore all the ones that are too big or too small. So that helps a lot. So basically see it as a two-dimensional partitioning. Yeah, you can first partition in one way and then kind of partition in the other way. It's just a little bit more relaxed. Yeah. Yes, and the next optimization is what's called batch mode. And batch mode was introduced with Column Store. Microsoft is now slowly starting to do a similar batch mode for Row Store. It's not as efficient as the Column Store one, but it's better than things. Yeah? So what happened in the past before batch mode, basically your results, your queries were processed row by row. Why? Because they were stored row by row, so it made sense to process them row by row. In Column Store, they are stored in buckets in the row groups, so it makes more sense to process multiple at a time, because it's most likely that you have to do the same operation over and over again, like adding up rows or something like this. Yeah? So what Column Store does, it takes about 900 rows. I think it's 936 right now, but that number might change. That's an implementation, that's not a definition. So roughly around 900 rows, and processes them in one go. So instead of take a row, process it, store it, the result, takes, process, store, take, process, row. Or they say, hey, let's take a pile of rows, 900, process them in one go, and move on. Yeah? This eliminates a lot of back and forth between the operators in your query plan, as you can see them. Yeah? So it moves instead of, like, you can imagine this in an office, instead of processing one page at a time of a document. So you go to the filing cabinet, you pick out one page, you go back to your desk, you sit down, you process it, you stand up again, and you file it in a different cabinet. Yeah? And if you do this 1,000 times, it will take forever. Yeah? But if you go to the first filing cabinet, yank out 1,000 pages, put them on your desk, process them all in as fast as you can, and then take the result of the 1,000 pages and put them in another filer, that's much more efficient than running between the two filers 1,000 times. Yeah? Yes. Why about 900 rows? It has to do with how modern CPUs work. Modern CPUs can do a single instruction on multiple pieces of data. Yeah? Microsoft choose an instruction set that can work on 256 bits at one. That's 64 bits times 4. Here we come back to the number 64, and that's why everything that, all the pushdowns, everything that you want to do is needed to be 64 bits or less, so it fits into these vectorized instruction sets inside the CPU. And this graphics here is borrowed from Bob Ward. Yeah, that in his thing is. So one batch, you have multiple columns, and you execute the same instruction across all of them, row by row at a time. Thing is. And if you take these about 900 rows per batch, you have 4 of them at the same time, plus a couple of header overhead, you end up with about 64 kilobytes in memory, and this is how much memory SQL processes Column Stores one piece at a time. You know? That's the explanation. Again, more details from Bob in his presentation, which is very good. Yes. So what about data types larger than 8 bytes? Column Store can process them, but it tries to compress them, but you will not get all or none of the features we talked about. So no aggregate pushdown, no filter pushdown, no row group elimination, and limited batch mode, because they just can't process it in one go. So they have to shuffle around the data across and loop through it. It's just not as optimal. It works, no question there, but you lose efficiency. Yeah. What I usually do is, if I have long strings or so that I need to do, is I put them outside in a reference table, and like a dimension table called star schema, snowflake schema, whatever you want to call it, put it outside, because for the actual queries and the reporting, you don't need the data. You can dereference that at a later point in time in the query. Archiving data. Column Store has 2 modes. regular compression and archive compression. Archive compression is much more thorough than the regular one and makes the data even smaller. Yeah, it comes at the price that it takes more cycles to uncompress and therefore is a little bit slower. Yeah? So that is between you and your storage cost if you want to do the higher compression and therefore save on storage cost, but then need more CPU to process the whole thing. Yeah, you have to test what works best for you. I have cases where we went with archive compression from day one, and I have cases where we had just some the current partitions in regular compression and the older partitions that are more like queried less often became archive. When you archive between two machines, if you archive even on the same machine, yeah, so if you archive like from one database to another database, and it gets much more, you will feel it much more if that other database is on another server. Yeah, if you move data from column store into another column store, it is unfortunately not done efficiently. So imagine we have a perfect row group where all the columns are the same for whatever reason. Yeah, so we have 1 million rows that basically compress into a single value that says we need this 1 million times. Yeah, when you move the data into another table or another database or another database and another table on another server, what SQL Server has to do is uncompress the whole thing, make it regular rows, move them over, and make them column store rows again. So I had a case where we compressed about 1 to 168. So 168 bytes in reality become 1 byte in the column store. Yeah? That was very good and expected because we had very repetitive data. The problem was when we moved it to the archive, the data that had to be transported was 168 times larger than the data we had stored on disk. And it doesn't sound like that much when you look at like a couple of rows. But imagine your data is 10 terabytes, and then you have to move it to the other machine and it gets 160 times larger. That 10 terabytes is suddenly 1.7 petabytes that you have to move through the network. And that's something that hit us by surprise because we didn't think about it. So be aware that if you archive to other systems, the data is transported uncompressed and unoptimized. Yeah, maybe Microsoft will give us a better solution in the future. I don't think so anytime soon. So far, they ignored all my requests, but you never know. Maybe someone hears it here and takes it to their heart to give us some tool things. Because technically, it's possible to, if you move like a whole partition or so, that we could just take the compressed data in the underlying table and just stuff it on the other side and fix the metadata. But not today. So keep that in mind. Backups. Strangely enough, clustered column store compresses a lot, but backup compression can squeeze out even more compression on that. So backup compression makes still sense, even if 99.9% of the database are compressed column store, an archive column store. Backups still make it smaller, so keep it on if you can afford the extra CPU cycles. Backup compression, I think it's because it's using the underlying blobs and regular metadata that these pages can still be optimized. And I also know that the backup compression in SQL Server understands page headers and stuff like this, so they know how to deal with that in a better way. So, yep, I still turn backup compression on. So, when nearing the end of the presentation, where are the limits? I don't know yet. I haven't found the limit, how big I can make a column store. And how things, yeah. The largest column store I worked on so far just had over 3 trillion rows when I saw it the last time. Yep, that's that number with that many zeros. It was about 15 terabytes on disk And that's where we started, hey, maybe we can archive that, and then learned that when we take the 168 bytes of data that are compressed um, down, and that it's suddenly much, much larger, and we don't want to have that. So this is the limit. It works just fine. Inserts are as fast at 3 trillion as they were at the beginning. And querying, since we partitioned and do all this, works still fine. And I'll explain that on the next thing. If we would not have column store and do this in row store, instead of 15 terabytes, we would need half a petabyte. And that is amazing how this helps us store so much more data that we could not store without that. I don't even want to know how much this is in something like XML or JSON, but I would say probably multiple petabytes. So where are the limits, part 2? For us, with 3 trillion row, we want to have a query result in 10 minutes or less. Yeah. So what we ended up optimizing for, we did count star, sum, average, min, max. We use push down aggregates as much as we can. Yeah, we try to optimize the queries, simplify this, change our data model so that we can do much simpler things. Often with column store, it makes sense to add a couple of additional columns with pre-calculated values to make queries simpler, because the compression makes them close to zero. So you're not adding that much data, but you're enabling us to simplify your queries and therefore make them much faster through the pushdown. We filter on a date and one more argument in our partition elimination. So we have date and a group of items that we query there. We have a second search argument query condition that we use all the time, where we do row group elimination. That's the one where we pre-sort the data for and try to stuff as many identical values in a row group as we can. We have another one on C where we just use filter pushdown. So usually we have 3 to 5 criteria that we filter on in most of our queries, and that's the one thing is. We have a couple of group bys usually, and for that we use the aggregate pushdown, and we make sure that the whole thing runs in the batch mode. So our column store, every column fits in 64 bytes, everything else is normalized out, and that works really well. So the 15 terabytes can be processed in 10 minutes or less on a, and this is the super surprising part, that stuff runs in a virtual machine. Yeah, with I think it's 8 cores, a couple of gigabytes of memory. So this is not high-end super duper equipment. This is a freaking VM running the whole 15 terabytes and working just fine. This is the magic of column store if you use it correctly. We've done it wrong massively in the beginning. We just did single row inserts. We deleted data. We updated data once we fixed error. We saw that we had captured stuff wrongly, and we made it horrible until we learned all that by experience and talking to people like Bob and Nico about it, I guess. So now, and again, this is me guessing, we're going to go into the Q&A where you can ask me either through chat or maybe even in-person questions, and I will answer them. If not, thank you very much and for listening in. Enjoy the rest of the conference. Again, here's my email if you have questions that you don't want to ask here or you come to your mind later once this session is over. Special thanks to Microsoft for sponsoring this event here, Data Platform Summit 2021. Thank you very much and have a great day. And there's some ways to win prizes, and please follow that. Is there anything else? Nope, we're done. Thank you very much. Have a great day.